Hello ladies and gentlemen, welcome to the portal. In this video we are going to discuss on how current affect the terminal potential difference. Okay, so the terminal potential difference is just a potential difference that you can measure across the battery using the instrument the voltmeter. Okay, so you are aware that we have EMF and we have terminal potential difference. So now what is the EMF? Okay, so EMF, it is defined as the maximum energy the battery can provide to move charges passed through it. Okay, so and V external, or what we say the terminal potential difference, it is a value that we can read and then that value tells us how much energy is available that we can use in the external circuit to move the charges. Okay, so now what I need you to be familiar with is this equation. EMF is equals to V external plus V lost, or what we call sometimes V internal. Okay, so inside the battery, as the battery is functioning, as the current is flowing, there are collisions between the chemicals of the battery. Some of the energy is converted to heat, so that leads to some of the energy being lost, so hence the term V lost. So we will see that we don't necessarily have 9 volt available to do the work to move charges. Okay, so we will have then less than 9 volts available when the circuit is working. Okay, so it is due to this energy being lost due to heat and collisions inside the battery. Okay, so now what I want is this. So we are going to make V external subject of the formula, and then I'm going to take V lost to the other side. So I'm going to have EMF minus V lost. Okay, so V lost, I can write it like this. I can say it is equals to I multiplied by the internal resistance. Okay, so what does this tells me? It tells me that, oh, that V external depends on the current that is flowing inside the circuit. Okay, so if the current changes, then the V external will change. So I don't have to worry about the EMF, I don't have to worry about the internal resistance, because the EMF and the internal resistance, they are what? They are constant. Okay, so the only thing that is changing is what? It is the current. Okay, so we can see now, oh, the V external depends on what? Depends on the current. Okay, so now since we saw that V external depends on current, so let's have a scenario here. So what happens when there is no current flowing in the circuit? So when there's no current flowing in the circuit, it means that I, it is equals to 0, isn't it? 0 amperes. So now it means that V external, it is equals to the EMF, because here the current will be 0. So here I'm going to have 0 multiplied by R, which is 0. So V external, it is equals to the EMF. You see, so now you must know this all the time. When the switch, when the main switch is open in the circuit, when the main switch is open in the circuit, the reading on the voltmeter across the battery will be equal to the EMF of the battery. Okay, So we can have a demonstration here. Here I have a simulation. Uh, Here I have a battery with an EMF of 9 volts and an internal resistance of 1 ohm. Okay, so now you will notice that the main switch is open and then there is no current flowing in the circuit. You see, there's no current flowing in the circuit. So I'm reading that the terminal potential difference is 9 volts, which is the same as the potential difference. The terminal potential difference is 9 volts, which is the same as the EMF. Okay. So now, what happens if I close the circuit? Let's go back here. Okay. So now, if I it is not 0, we know that I will not be negative, right? It will be positive. So EMF minus a positive value IR. Okay, it will imply that there are volts which are lost, because we know that V external it is equals to EMF. It is equals to EMF minus V lost. You see, so it means now there will be volts which are lost. So now what are we going to get? We are going to get that V external will be less than the EMF. Okay, so we are going to read a value which is less than what is advertised on the battery. So if you can check here, let's test it. Let's close the switch. Now the current is running, the current is flowing through the circuit. So as you can see, from 9 volts we moved to 8.18 volts. Okay, we moved to 8.18 volts. All right, so now it means that V external, we moved from 9 volts minus V lost, so we can actually work out how many volts were lost or how much volts were lost. Okay, so V external we are reading 8.18 volts, isn't it? Okay, so we can work out that, oh, okay, then it means V lost is what? 9 minus 8.18. Okay, so meaning 0.82 volts were lost. Okay, so you can see now that when the circuit is running, or let me say when there is current flowing in the circuit, V external is less than the EMF. Okay, now let's proceed. So in the circuit that I have drawn, I have two resistors connected in parallel series. So when switch 1 and switch 2 are closed, these two resistors will be connected in parallel series. Not parallel series. I'm sorry about that. In parallel connection, not parallel series, right? They will be connected in parallel. So what do we know about parallel connection? We know that when resistors are connected in parallel, the effective resistance will be less than the smallest resistor, will be less than each of the resistors. Okay, that's pretty dangerous to say the smallest resistor, but let me say here I have 10, here I have 10. Okay, so now the effective resistance will be R1 R2 divided by R1 plus R2. So now here I have 10 multiplied by 10 divided by 10 plus 10. Okay, so meaning I have 100 divided by 20. So meaning it's 5. You see. So what happened? So when I close switch 2, the external resistance is going to decrease. It means that now when switch 2 is closed, what happens? R external decreases. Okay, and we know that according to the relationship, I is inversely proportional to the resistance. So when R decreases, I increases. You see, and we know by now that when I increases, V lost increases, and then V external decreases. You see, so R external decreases, I increases, and then V lost. What happens to V lost? V lost increases, and V external decreases. I will show you what I mean. Okay, let's go back to the simulation and see what happens. So as you can see now that here we have 8.18 volts. What happens if we close the switch? Will the current, let me not talk about that, will the reading on the voltmeter increase, decrease, or remain the same? Okay, also note the current, right? So now the current is 0.82, right? So if I close here, so now I have a parallel connection. Notice that the current has increased. It has increased from what? From 0.82 to what? To 1.5 amperes. So now note that the terminal potential difference has decreased. Can you see that? So it testifies what I was saying. So theoretically, let's try uh, to to answer it theoretically. Okay. So here's the question. The question says that what happens to the reading on the voltmeter if switch 1 closes? Choose increase, decrease, or remain the same. Okay, so this one we've already simulated it. Okay, so we know that the reading on the voltmeter will what? Will will decrease. Okay, we've already showed that when. So the reason when there is current flowing, in the circuit, in the circuit there will be lost volts. Lost volts. Thus, V external will decrease while the EMF remains the same. Okay, so with an 8 of an equation, what I mean is this. So if now I have this, it means I have V lost, meaning for what I had, let's say I had 9 volts. So now I'm going to minus something from that 9 volts. So it means that I will have some the potential difference that is less than 9 volts. You see? So let's check another question. So here they say switch 2 is closed. Will the reading on the voltmeter increase, decrease, or remain the same? So give a reason for the answer. So number 1, we saw that the reading on the voltmeter decreased. Okay? So now, if they ask you theoretically and you don't see the simulation, what will you say? So it all depends, and it starts with the resistance. Okay? So step by step, we go step by step. So when we make a parallel connection, R effective decreases. Okay, so R external decreases. Okay, when R external decreases, the current increases. Okay, so when the current increases, it means there will be volts which are lost. So V lost increases. So when V lost increases, we know that V external depends on V lost, while EMF remains constant. So now V external decreases. Why do I say that? Because we know that we have this relationship, and we know that V lost is equals to IR. You see, so when I increases, V lost increases. So when V lost increases, it means we have to minus something that is larger from the EMF. So meaning we will have less volts left for us to use in the circuit. You see. So this is the reason when the external, or what we call the total resistance decreases, or what we call the load, when the load decreases, therefore the current increases, and then there will be more volts which are lost, and then V, the reading on the voltmeter, will decrease. Okay, so now here, now we can answer this one. Will the reading on the voltmeter increase, decrease, or remain the same? So because of this, we know that, oh, the reading on the voltmeter is this V external. So the arrow is going down. It means that it will decrease. So we will choose decrease. Okay. So now, giving reason for the answer, this is part of the reason, but we will write it like this. So we write now. Total resistance, or what, external resistance increases. Total resistance decreases. Okay, and then what? Current increases. That's the total current. Current increases. Okay, and then we know that, oh, it is explained by this. Okay, so when the current increases, EMF remains the same. Okay, EMF remains the same, and then V lost increases, and then therefore V external will decrease. Okay, so if they say with the help of an equation, this is the equation that we're going to write. V external is equals to EMF minus IR, or minus V lost. Okay, so this is how you answer such a question. Okay, guys, meet me in the next video. We will talk about power. Yeah, thank you.